Have you ever really stopped to think about what actually happens when an operator clicks a simple pump icon on a control room screen? We honestly take these digital interfaces for granted all the time. But in industrial control systems, the stakes are incredibly high. A poorly designed, laggy interface doesn't just mean you have a frustrated operator on your hands. We're talking delayed reaction times, missed alarms, and in the absolute worst-case scenarios, total system crashes. So in today's explainer, we're going to break down the exact architecture you need to build a rock-solid, high-performance operator station interface right inside SIMATIC Pcs7.
Okay, let's dive right into this. To wrap our heads around this complex software, we're going to use a simple roadmap. We'll be covering 5 key areas today. First, the interface architecture. Second, graphic objects and assets. Third, powering the dynamization engine. Fourth, compliant operator navigation. And finally, infrastructure and system health.
All right, let's kick things off with Section 1, the interface architecture.
So, process pictures in PCS7 don't just magically appear out of thin air, right? They are intrinsically tied to your plant hierarchy over in the SIMATIC Manager. When you go ahead and execute that compile OS function, the system does something pretty cool. It automatically generates your foundational graphic elements. We're talking default block icons for your tanks and valves, and it drops them straight into the Grax directory. But if you want to create a truly customized UI layer, you're going to need some manual intervention. That's exactly where engineers step into the WinCC graphics designer to add specific static objects and custom layouts that, frankly, an automated system just can't predict.
Moving right along to Section 2, graphic objects and assets.
Once you're actually inside the graphics designer, engineers pull from a very specific taxonomy of visual building blocks. You've basically got 4 main categories: standard objects, smart objects, Windows objects, and tube objects. These are your raw visual assets, the fundamental pieces that are going to make up your entire digital plant.
And this brilliantly illustrates how stark the differences really are. Standard objects? Those are just your basic geometric shapes and labels. Windows objects give you those familiar OS controls we all know, like sliders and buttons. But the real magic happens with the other two. Smart objects are fantastic because they come with ready-made dynamics. They literally feature built-in process I/O interfaces so you can effortlessly link them to your tag data. And then there are tube objects. These are not just static flat lines. They use specialized polygon functions with targeted fill patterns to create a really intuitive 3-dimensional representation of your plant's interconnected piping.
Now, as interfaces evolve, the assets have to evolve too. You absolutely aren't just limited to basic shapes anymore. Pcs7 offers some seriously advanced interface assets, specifically through its library system. The global library gives you all your traditional process graphics, sure, but the real game changer in modern versions is the SVG library. SVG stands for Scalable Vector Graphics. These are completely scalable, write-protected graphics that are absolutely perfect for web-based or mobile terminals. Why? Because you can zoom in infinitely, and there's zero loss of resolution.
Let's move under the hood for Section 3, powering the dynamization engine.
Okay, so we have our surface drawn, but it's just sitting there. It's completely static. Let's look at how this all actually comes to life through the dynamization pipeline. Imagine you have a raw input tag, let's say a temperature reading of 430 degrees. That data passes through a math engine, like a dynamic dialog, which calculates a percentage and then outputs a visual result. Maybe it fills up a thermometer graphic to 50%. But listen, you really need to pay attention to a critical constraint here. You can only adopt the colors of these objects dynamically if the property Global Color Scheme is explicitly disabled in the Effects menu. If you forget and leave that enabled, your dynamic color logic will literally just be ignored by the system. It's a common trap, so watch out for it.
When you're choosing exactly how to make these elements move or change color, you basically have 4 main methods, and picking the right one is absolutely vital for your system's health. A simple tag connection or a direct connection, that has a very minimal system load because it's just passing a value straight through. A dynamic dialog is awesome for interpreting values or setting color thresholds, and it still keeps the system load really low. But look at C or VBS actions. These are event-driven or cyclic scripts. Yes, they can handle highly complex logic, but the system load they generate is incredibly heavy.
Which brings us to a massive, flashing red light warning for any control engineer. Using heavy scripts severely impacts your picture opening times. This is an absolute, non-negotiable architectural rule in PCS7. You must relocate heavy cyclic computing operations down to the automation system, the AS. Never ever execute heavy cyclic scripts on the OS. The operator station is built for visualization, not for doing the heavy lifting.
So why is that rule so strict? Well, it all comes down to trigger behaviors. A cyclic trigger operates on a continuous polling interval. It's basically asking the system, what's the value every few hundred milliseconds, regardless of whether anything actually changed. It's exactly like an annoying kid in the backseat constantly asking, are we there yet? Are we there yet? This rapid, continuous cycle severely bogs down your performance. Contrast that with a tag trigger. A tag trigger is highly efficient because it only queries the system when the actual underlying variable updates. It just sits quietly until the tag says, hey, I've changed, which keeps your overall system load remarkably light.
All right, Section 4, Compliant Operator Navigation. Now that our interface is built and efficiently dynamized, the operators actually need to move through it. And I get it. It's super tempting to just drag and drop a target picture onto a button to create a quick, direct mouse click connection. But in PCS7, that is strictly non-compliant. Doing that creates hard-coded navigation, which means the OS has absolutely no idea where the operator came from. There's zero history tracking. Instead, you've got to use dynamic wizards, specifically the Picture Exchange in Workspace wizard. This automatically writes a compliant background C action that unlocks the full suite of OS navigation features, like jumping back to previous picture. Plus, if you apply this compliant navigation to those tube objects we talked about earlier, operators can intuitively trace the physical flow of material just by clicking upstream or downstream flow paths right there on the piping. It's incredibly smart.
Finally, let's zoom out for Section 5, Infrastructure and System Health.
We're now looking at our third and final pillar. We've built the surface and we've tuned the engine. Now we have to talk about the lifeline. Because, let's be real, all those beautiful dynamic graphics mean absolutely nothing if the back-end communication fails. The beating heart of this lifeline is the LifeBeat monitoring system. Your operator station server continuously checks the health of the entire plant network. It does this by constantly pinging nodes. That includes other OS clients and the underlying AS systems, using OPC and S7 protocols. If any single node fails to answer that continuous ping, the LifeBeat system immediately generates a central process control message. It alerts the operator instantly that a piece of the architecture has gone dark.
But just detecting a failure is only half the battle, right? Diagnosing a massive system trip requires extreme chronological accuracy. During normal operation, the system establishes a baseline by receiving what are called 10-second grid telegrams. But then, let's say a major system trip happens. Boom! A message surge occurs where hundreds of alarms suddenly flood the system in an instant.
This exact scenario is why high-precision timestamping is absolutely mandatory. When that huge surge of messages hits in the exact same millisecond, you have to know what broke first. Because the CPU's integrated Ethernet interface is set to receive those precise grid telegrams, it essentially lays down an identical chronological grid across the entire plant. This allows the system to definitively sort through those hundreds of alarms and identify the exact originator of the cascade. Trust me, this saves hours, if not days, of painful troubleshooting.
To maintain that perfect synchronized chronological grid, you have to sync the time across all your devices. Now, you can use NTP mode, which relies on an external server. And hey, that's totally fine for basic PC networks. But for a highly integrated control system, Somatic mode is the absolute standard. In Somatic mode, the WinCC software sitting on the OS server acts as the ultimate internal time master. It actively pushes the exact time down to all automation systems via the plant bus, ensuring every single controller is ticking on the exact same millisecond.
Okay, let's take a breath and synthesize everything we've covered today. We've essentially built a complete framework out of 3 pillars. First, we started with the surface, auto-generating our foundation and manually customizing our graphic assets. Second, we built the engine, carefully selecting our dynamization methods to keep the system load light while still bringing the process to life. And finally, we secured the lifeline, ensuring robust LifeBeat monitoring and flawless time synchronization across the entire network.
And this brings us to our master summary of the PCS7 customization architecture. A truly stable OS interface is never just a gritty picture. It is the careful, calculated combination of highly efficient graphical dynamization on the front end, fully backed up by flawless, high-precision chronological synchronization across the plant bus on the back end. You literally need all 3 pillars: the interface, the dynamization, and the infrastructure working together in perfect harmony.
Which leads me to ask you this final question, something to take back and really think about in your own control rooms. Is your plant's interface just a surface-level drawing patched together with heavy scripts, or is it a fully synchronized, highly efficient architecture?
I highly encourage you to take a look under the hood of your own systems and see exactly how these master rules apply. Thanks so much for joining me on this explainer, and keep learning.